How do you know?
Cesium's big.
Cesium's big, right? It's got more electrons, and so the cesium is going to be bigger than the chloride. So say well, this is difficult, but say that sodium chloride and cesium in our and cesium chloride, or sodium and cesium, have the same electronegativity. So say they both have an electronegativity of 1. What's the electronegativity? Oh, then chloride. 3.16, 1.0, 3.16. Of course, them having the same electronegativity is not true, but let's say in our thought experiments they do. We already know that the bond distance of cesium chloride is greater. Which compound has a higher dipole moment?
Sodium chloride.
Give me a firm answer.
NaCl.
Has the higher dipole moment? So what goes into dipole moment?
No. The
Distance, right? Dipole moment equals the charge times the distance, right? So the electronegativities are the same. That's telling you that the charge is probably the same, right? Or you could say +1, +1, -1, -1, -1. So what has a greater separation of charge in this case? Cesium chloride or sodium chloride?
cesium chloride.
Cesium chloride has a greater separation of charge, right? If sodium and cesium carry the same charge, +1, or they have the same electronegativity, and of course chloride's the same, if the +1 and -1 is separated more in cesium chloride, because the bond distance is more, the dipole moment of cesium chloride is going to be higher.
And the van der Waals forces will be lower because it's 1 over R26.
Yeah. So the force between cesium chloride, because they're a little bit further apart, the van der Waals forces will be less because they're further apart. Yeah, if they have exactly the same charge. So, just let me ask one follow-up question. Does everyone get what a dipole moment is? Remember the charge and the separation. So electronegativity or the charge or something like that gives you the charge, and then the separation. And remember, it's a linear combination of the two. So you move it, some species further apart, and that will give you a higher dipole moment. Question?
Is the charge of an electron, or is it the charge of the atom?
It's the charge on the atom. So it can be the charge of an electron if cesium has a formal +1. It can be the charge on an electron, right? Because that's a full electronic charge right there. So if the electronegativity of cesium is 1.0 and the electronegativity of chloride is 3.16, it's probably not a full charge, right? Because we know that +1 and -1 are just convenient numbers to write. Usually it's +0.2, -0.2, something like that. But just the idea that the dipole moment is both the charge and the separation is enough. Yeah.
The charge is only on one, like the positive cesium, or is it on cesium and chloride?
It's the charge separation. So how far are the charges separated? Because what's the overall charge on cesium chloride? 0, right? So if you have a plus 0.2 here, you have to have a minus 0.2 here.
So how do you know what the charge is again? How do you find that?
Oh, so the charge, so in the simple experiment, let me just erase this for a sec. So the simple assumption when you think about cesium chloride, cesium is +1, Cl is -1, right? And so we can take this as a simple estimate of the charge, and then all we need to know is the separation distance. And so we're not going to, in this class, we're not going to compute partial charges or anything like this. So you won't have to know that cesium is actually plus 0.5 and chloride is minus 0.5, anything like that. Those numbers come from the electronegativity or the measured dipole moment. But if I asked you something like, right, comparing the dipole moments of these, and we said that the bond distance of R is smaller here, we'd say that cesium chloride has a higher dipole moment because it's got the positive one and negative one. So that's the most important part, is just the whole charge or the oxidation state of these two elements. Yeah?
Going off of that, if you throw in like a row 2 metal, so then like magnesium has a +2 charge and 2 chlorines, how's that going to change the dipole moment?
Yeah. So if you have magnesium, which is +2, and you have a chloride here, and then wherever the other chloride resides, what's the dipole moment here?
Yeah. Are they going to? I guess they won't cancel out, but do you just have like one strong going this way and one going this way?
Yeah, you know, it's a good question that I don't exactly know how to compute the dipole moment for this sort of thing. I think you could take the dipole of just magnesium and one chloride, right? Because here you have charge separation, or you have, you know, if it's magnesium, then chloride's here, and then you have another magnesium here, and you need, let's see, 1, 2, you know, the chloride's going to be over here. You have to take a slice of this thing to figure out what dipole moment you're talking about. Because if you take this, all of a sudden that thing's symmetric, right? And that charge is 0. So it's hard to compute a dipole moment for that.
Okay.
So I think you need to know what piece you're talking about. There's actually a dipole moment of these three right here, because this acts as a negative. Then there's your positive up here. So that has a dipole moment. But that's a harder situation to compute.
Okay. If we just take that one side of it, and then you have like a sodium chloride, and you assume sodium and magnesium are similar size because they're next to each other, you would say magnesium chloride has a larger dipole because its charge is greater.
Oh, so you want to compare the
or is that
dipole moment of magnesium chloride versus sodium chloride? Yeah, I don't know how to do that. Yeah, because of what you brought up, right? What's, you know, versus NaCl, that's easy, right? It's easy to think about what the dipole moment looks like right here. But this, I'm not so sure.
Okay.
Yeah. Yeah, go ahead.
Can you explain this bullet that says on the study sheet, FTIR, UV vis, absorption and transmission spectroscopy?
Sure.
I'm kind of confused about that stuff.
What's that?
I'm kind of confused about all that stuff.
Yeah. So did you look at the notes?
Yeah.
Okay. So let's say you have absorption, you have UV vis wavelength, and you have a compound like this, right? And this is 300 nanometers. So this compound has a strong absorbance at 300 nanometers. How do we know that? The absorbance is high, right, at a given frequency. And so all you need to know about this spectroscopy, so at 500 nanometers, does this compound absorb much light at 500 nanometers? No, right? Its absorbance is low. What does the transmission spectrum of window glass look like in the visible range? First, what's the visible range?
Colors that we can see.
Yeah, so give it to me in nanometers, the colors you can see. 350 to 700 nanometers. Transmission spectrum of glass, high transmission, right? In the visible region. 90, So the point about the spectroscopy, so what causes high transmission, or what causes absorbance in these different molecules? Does anyone know?
Refractivities?
Vibrations, specific functional groups in the molecules, you know, so let's say aromatic rings are double bonds, right? So these double bonds can cause adsorption features. There's nothing in glass that has strong adsorption at these wavelengths. That's why glass is clear. But if you have, let's say, if you put in black particles, right, or you paint the glass black, you're actually putting down molecules that absorb the light, right? And so you have some strong adsorption of bonds, or it could be aromatic rings, or carbonyls, or whatever. You're putting in features of the molecule that will absorb at a given frequency. And you don't need to know what those are. So you don't need to know that double bonds absorb at 300, or you don't need to know that, what the components are of glass that allows transmission. What's the elemental formula of glass? Does anyone know? Yes, SiO2, right? And so there's nothing in SiO2 that absorbs at these wavelengths. And so the whole point about thinking about the spectroscopy part is that if I say, okay, you're studying a certain material, say you're studying zinc oxide, and zinc oxide absorbs strongly at 1500 wave number in the FTIR. What does that plot look like?
Absorbs highly.
Absorbs strongly at 1500.
So the curve would go up 1500.
Yeah. 1500 wave number, right? Units. Absorbance. So make sure that you tell me what the X and Y scales are. I think I've asked you to draw sketches before, like the ionization energy of aluminum, right? I asked you to draw me a little plot. And of course, when you're doing homework, you can look up the ionization energies of aluminum for first, second, third, fourth, fifth.